Hello, my name is John Dennis and I'm Master Black Belt with the International Lean Six Sigma Institute based in Cambridge, England. And I would like to demonstrate to you today a new classroom game that has been developed especially for this period of COVID-19, in which group activities are not as easy to perform. And we need to have an example of a process that can be done in class by each student where it is not a group activity. So what I want to show you is a layout, a setup for a game that can be done by trainers of Lean Six Sigma quite easily without too much expense, and it will get the points across about the main principles and tools of Lean Six Sigma. It will teach people about process, about inputs, about outputs, about customers and suppliers. It will teach them about 5S, visual management, mistake proofing, poka-yoke. It will teach them about the voice of the customer and what is critical to quality. It will also teach them problem solving skills, and where you can demonstrate the use of the fishbone diagram, 5 whys. You can use it for process mapping, value stream mapping. Most of the main principles, tools, and techniques of Lean Six Sigma can be demonstrated using this game that students can follow along in the classroom. So I just want to show you what it is now. I'm based in Switzerland right now because I'm going to be putting on this class in just a week's time. So I thought I'd take the opportunity to make this short video to show other people how to use it. So what we have basically is 3 different colors of Play-Doh. 3 different colors of Play-Doh. We have our tools, rollers, cutters, some different types of rollers here, and 2 different types of cutters, like pizza cutters. We also have these cookie cutters here. So these are star-shaped plastic, and we have, very importantly, a digital scale that will weigh to 1/100th of a gram. So the end result is actually a star which has 3 different layers, and I'll show you a photograph of that. But what you do is create 3 different colored balls of 3 different sizes from the Play-Doh. Now the instructions say that the target value for the small ball is 10 grams, the target value for the medium ball is 15 grams, and the target value for the large ball is 20 grams. We give a tolerance limit on either side of that target value of 2 grams. So in other words, the green ball can be from 8 grams to 12 grams. The orange ball here can be from 13 to 17, and this purple ball here can be from 18 to 22. Those are what we would say are the engineering design limits for these inputs. Now, digital scale then to test whether you have got the right size for each of those inputs. Okay, so you would be basically rolling the ball out, taking some Play-Doh, rolling the ball, tarring, making sure you've got the right grams and tar on the scale, and weighing it, and that says 10.22 grams, 10.22 grams. So that would be within specification limits. According to the original process, we would go ahead and use that as one of the inputs because it's within the tolerance limits, the design tolerance limits. So a bit of 5S there. Okay, this was an example one. We don't need that at the moment. So next step in the process, this is a value added step. A value added step is to roll the Play-Doh. Now, we're going to cut this using the small ball. We use the small star for. So we have 3 different sizes stars. We're going to use the small star to cut a star out of the green Play-Doh. Okay, so I'm going to remove the excess here, and we have what we're left with, a green star. You see that? You're left with the green star. Size ball is the 15 gram, which we would have already weighed to make sure it's within the tolerances. We roll the 15 gram. We take the second size star, we cut that, we remove the excess, and now we have 2 stars, the small one and the medium sized star. Step is to take the large, and we're going to roll that. This is more Play-Doh, but it also has to be spread out more because the star you're going to cut is larger. Okay, so I'm now going to cut this star with the large cutter and remove the excess. So now we have the three different size stars. The process for assembly is to take, you have to be careful as part of the process to be able to peel the star from the surface, and there's going to be some problem solving that needs to be done to understand the best way to do it. Okay, so there's some process improvement can be done to make sure you get that star correct. So we have the purple star. The assembly is to create a 3-layer product. Now this could be in manufacturing something to do with semiconductors, electrical thin films, anything where you've got different materials that have to be bonded together or combined together. Now this has to be placed on the bottom star so that it is concentric, and I'll show you a finished product in a minute. But as well as possible, this needs to be placed on there. And in the class you'll have people that come up with different methods for doing this, and you've tried to find what is the best method to create something that is concentric like that. So if you can see that is the aim there. That is the aim of that particular step. Star, and we're going to peel that off. And we're going to place that on top of the orange star. Now, you want to be right first time. So as you can see, that did not go on first time in the right position. So these are things that in the class you want to be thinking about as far as problem solving techniques for getting concentricity among the stars. So we have achieved there the next step, which was to form the layers. And the more concentric it is, the more that those stars line up, the better the quality. The more the customer is going to be satisfied. Okay. As I say, we have a product there. We have a finished product, and you can do all sorts with this game. You can be measuring cycle times of each step. You can be measuring rework, you can be measuring scrap in terms of how much plasticine is left over. And because we have the digital scale, you can be quantifying this in terms of quality. We can be using other measurement instruments like vernier calipers, for example, or even just rulers to measure distances to see how concentric it is and come up with metrics for concentricity. So I'll just show you the tolerance limits that I set for the star. So I will share screen with you here something. Shown on the screen at the moment are the tolerance limits for the input balls of plasticine. That before you roll it, they should be 10 grams, 15 grams, and 20 grams. Okay. Now, after you've assembled the star, the specification limits are that the total star should have a target of 10 grams. That is, all three of them together, the finished product should be, as you can see on the screen here, 10 grams. And we're giving, again, a 2 gram tolerance limit on each side. So it needs to be between 8 and 12. But the closer it is to the nominal value of 10, the better. Okay? So as you can see there, that says 6.47 grams. 6.47 grams. That particular output has actually not come within the specification limits, right? That would have to be scrapped and reworked. All of the raw materials can be recycled, but think of all the time that took. So what do you have to do in your process to improve the inputs? What do you have to do? Is it the tools you're using? Is it the method you're using? In order that the output is on target at 10 grams, or at least to start with, we try to get it between the specification limits. These are the things that this exercise bring out. These are some of the questions that are asked. Now, in this particular case, because the star is too light and the customer is not getting the weight that is expected, one of the input changes that would be needed to be made is to do the rolling process so that each layer is a little bit thicker. And that now has to be part of the process, part of the standard operating procedure, that each layer is slightly thicker. Once you have a process which gets the correct thickness of each layer such that the output weighs 10 grams, then you start having a standardized procedure. But still there's going to be variation, so you can use this for measuring variation, for doing capability analysis, for doing control charts. It lends itself to all sorts of statistical tools as well as lean tools. So I hope that this explained the game, and that you will get some benefit out of this. So I'm John Dennis with the International Lean Six Sigma Institute, that is ilssi.org, and myself or one of my colleagues will be happy to help you, or any questions you have about this particular Lean Six Sigma training game, which we're calling the 3-star game. 3-Star Corporation is the company that's making this, and you can make this as if it's a decoration for a cake made out of icing, or you could consider these to be layers of wafers, silicon wafers in some sort of electrical component, or silicon chip manufacturing, or in transducers with different thin films of metal. It lends itself to all sorts of scenarios. So good luck, and good luck with your Lean Six Sigma training. Thank you.